Hey guys, I want to go over with you today what you all did in Chapter 7. In Chapter 7 we looked at the pre-algebra basics, and I'm just going to kind of go through each of the little things that we covered in that class. It started with really trying to get to know all of our integers. That it started off by showing us, and in fact, I'm looking at the bottom of page 165. It started off by showing us this number line. If you recall from the very first day of class, we drew a number line on the board, and it shows you how these numbers fall in counting order. Obviously, I could go on forever, but we're stopping there at 4. The number line then shows us, if we were to look left of 0 on the number line, how our negative numbers will fall. Again, we could go on and on forever on that too. What the number line shows us, it shows us how these numbers fall in counting order. Again, 1, 2, 3, 4, 5. I could go on for days. But if I go left, you see I'm kind of going in the same fashion. I'm looking at, 1, 2, 3, 4. I would do the same thing, but I'm just going to the left now. By adding this negative sign in front of each of these integers, what it shows me is I'm getting smaller and smaller and smaller as I'm going left. A way to think about that, I always relate integers to money. If I think of these numbers over here on the right, these positive integers, they're positive, and they indicate, if we're looking at it in terms of money that I have. That if my bank account said this right here, said $4, then that means that's $4 that I have in my account. Whereas if my bank account said this over here, -4, then that means that's $4 that I owe the bank. So that's less money that I have. So that's a way to think about it in terms of this number line here, that if I were to keep going way far down that number line, and I went all the way to -892, then if my bank account says -892, then I have a whole lot less money than I would if I had $4. So again, as you go left on that number line, my numbers are getting a whole lot smaller. As I go right, my numbers are obviously getting bigger. So that's what the purpose was of this number line, to show us how we can relate our integers to one another. So there's a couple of different things we'll do with this number line. But as we go through each of the different sections in Chapter 7, I want you guys to get a better understanding of what these integers mean and what we can do with them. If you flip over to page 164 in your book, a couple practice things you can do. Throughout the chapter, we'll be able to, like in practice 1, what we're doing there is we can use different words, different phrases to indicate whether or not we're dealing with a positive or a negative. Later on in the chapter, we'll be able to look at different phrases, and we can use those phrases to represent either addition, subtraction, multiplication, or division. But we're going to use very similar phrases right now just to tell us whether or not we're dealing with plus or minus. So for instance, number 1 says, I have 18 more nurses. Well, more is something that indicates a positive. That's a good thing. So I have plus 18 in that case. Whereas if it had said if it had said 18 less nurses, I would have indicated that with a -18. So that's what we're doing in each of those. We're just kind of indicating whether or not it's a positive or a negative. So for instance, then number 4 on the same section says a 12-pound loss in weight. Since it's a loss, we would indicate that as -12. So that's what we can do. We'll see that later on in the chapter, where we can take those word phrases and turn them into algebraic expressions. On the next section, on the same practice 1, number 6 through 10 is asking is asking us to get into the opposites of each integer. And we actually have two opposites written on the screen here in front of you. 18, or positive 18, and -18. The opposite of any positive is that number's negative, whereas the opposite of any negative is that number's positive. One thing I want to also mention while I have this up on the screen for you guys, you'll notice that for positive 18, I wrote plus 18. You guys can see that right here. But I also want to point out on the number line, I didn't have to write plus in front of that 1 through 4 up there. To write any positive, you don't necessarily have to put a plus sign in front of it. Had I have just put 18 there, that would have been just fine. If I had just taken off this plus sign in front of that 18, 18 by itself still indicates a positive. But to represent a negative number, you have to put the negative sign in front of that number. So, for instance, you can see I have two opposites here. Positive 18, its opposite there is negative 18. Well, down here where it says negative 12, the opposite of that would then be positive 12. Well, I can write that as just 12, and that still represents positive 12. So, on each of those, like number 6, for instance, negative 16, its opposite would be 16. Or if you wrote positive 16, that would be just fine too. So those are what opposites are, and opposites are great because opposites are going to help us later on when we get into subtraction. So I would remember that for the subtraction. Okay, I'm going to leave that number line up there because now I wouldn't worry too much about on page 165. You can compare them. You can compare, like I said, if you remember that as we go left on the number line, my numbers are getting smaller. As you go right, your numbers are getting larger. So had I have asked you to compare positive 6, for instance, to negative 6, obviously positive 6 would be down here somewhere on the number line, whereas negative 6 would be somewhere over here. So positive 6 is larger, so we would indicate that as greater than, as we've done before. We're used to seeing those. Okay, so remember that we have those to represent are greater than, less than, and equal to. I know for me, I probably won't see, I won't use that on a test, so I wouldn't worry too much about that. But I left this number line up here for a reason. The next section on page 165 is getting into the absolute value. The absolute value of a number, just by definition, now this is something that you're not going to be asked to define later, but it's good to know what this means. It's going to help us when we get into our addition of these integers. The absolute value of any number is simply just the distance from 0 on a number line. So you'll see in your book the way that they asked for absolute value is they put these two brackets around a number. So if I was asking for the absolute value of positive 3, you'll see how it's written there on your screen as these two brackets around the number 3. So what is the absolute value of 3? And again, I had said that means the distance from 0 on the number line. Well, here's 3 on our number line. So what I mean by distance is how many spaces away is 3 from that 0. Well, if we count, 0 to 1 would be 1, to 2 is 2, and to 3 would be 3 spaces away. So my answer here is then 3. The absolute value of positive 3 is just 3. If I asked for the same scenario, if I asked for the absolute value of 3, but this time I'm asking for, excuse me, the absolute value of negative 3. Now this is a little bit different, kind of. The absolute value of negative 3. Here's negative 3 over on my number line, but the definition is still the same. I want to know how many spaces away are we from 0. So 0 to negative 1 is 1, to negative 2 is 2, to negative 3 would be 3 spaces away. So the absolute value of negative 3 is simply just 3. So you can see the pattern we have here, that really the absolute value of any number is that number, but it's not a positive or a negative because it's the number of spaces. If I asked for the absolute value of, say, I don't know, 487, well, that would be way down here, but I know that it would take me 487 times to get there, so the absolute value of 487 is 487. It would be the exact same thing if I asked for the absolute value of negative 487. Then it would simply be 487. So again, you'll see that the absolute value of any number is always just that number without a sign on it. So in your book on page 166, you'll see I'm asking for the absolute value of positive 12. Well, the absolute value would just be 12 because it would be 12 spaces away. Whereas in number 2, the absolute value of negative 14 would be then 14. So again, you're seeing just that value. And again, that's going to help us when we get into our addition of our integers, which we're going to get into right now. So we'll get into these integers, but when we go into these operations, there are some rules to remember with these operations. So as we go through these, I'll write down the rules on the screen so you guys can have those and for your notes as well. The first thing we're looking at is addition of integers that have the same sign, meaning they're either both positive, the two numbers that we're adding together, or they're both negative. So let me give you an example. for one here. So if I have, let's say, positive 7, and again, I just have to write 7, plus positive 5. We've seen this before. We know what 7 plus 5 is. 7 plus 5 is 12. We're aware of that. But what we have on the screen here, if we're thinking of it in terms of integers, is positive 7 plus positive 5 is positive 12. So what actually happens when we're adding two integers of the same sign, we're going to go ahead and add those together just as we always would, but we're going to keep the exact same sign. Therefore, I would get a very similar in kind of the same aspect there. If I had negative 7 plus negative 5, then we're going to see that. We're going to see negative 12. My rule for adding integers of the same sign is to go ahead and add them together. So 7 plus 5 is always going to give us 12. And keep the sign of that problem. So the first one, they were both positive, so my answer was positive 12. In the second one, they were both negative, so my answer was negative 12. So, and another thing I want to point out, if you ever see this, if you ever see little brackets placed around numbers, don't be thrown off by those. Your book is simply just doing that to keep you from, if you didn't have those, then your eyes may see the plus right next to the minus, and it may get confusing. So your book simply puts the parentheses around that negative 5 to show that it's negative 5, not necessarily minus 5. So it just makes it easier on the eyes. But you didn't necessarily have to have those parentheses there, because even without, you can still see that that's negative 7 plus negative 5. Anyway, so again, another thing that I had mentioned to you guys earlier is that if we think of integers as money, positives being money that I have, negatives being money that I owe, in both of these scenarios we can think of it that way. So in the blue at the top, the positive integers up there, again, if I look at positive 7 as me having $7, positive 5 means I have $5. Well, let's think about that scenario. If I have $7 in one pocket and I have $5 in another, then that means I have a total of 12. So that's why we ended up with positive 12. Same scenario down at the bottom, except I'm looking at negatives as money that I owe. So let's say I'm going to a store and I'm purchasing something that's $7. So I owe $7 for it. Another item that cost me $5, so I owe $5 for that item, meaning that I'm going to owe a total of $12 when I put these two totals together. So you can see here that that's where we got that negative 12. So that's adding integers of the same sign. Again, my rule is to simply just add them together and keep the sign of those two integers. Okay, so let's take a look at my next rule now. My next rule says that if I have opposite signs, so if I have opposite signs, what I'm going to want to do here is let me give you a scenario and then I'll show you the rule. So let's use the same two numbers. Let's say I have positive 7, but this time I'm adding negative 5. And I'm going to put a little parenthesis around here to show that is negative 5, not plus minus. But let's think of our scenario that if I said that positives are something that I have, then what I have here is $7. But I'm at the store and I'm purchasing something that's $5, so I owe $5 for something. So what do I leave that store with? If I have $7, but I owe $5 for something, well then I'm going to leave that store with $2 still left in my pocket. It would be the opposite if this was the opposite scenario. If I had negative 7 plus positive 5, so again, still opposite signs, a negative and a positive, but this time I'm looking at it this way. I owe $7 for something, but I only have 5. So if this is the case here, then what do I leave that store with? Well, I know technically I wouldn't necessarily leave that store because I wouldn't be able to purchase that item because I still owe another $2. So that's why the answer here would end up being negative 2. So when we have two integers of the opposite sign, then what happens in this scenario is you can either look at it like this, look at it as money, and that's an easy way to put those together. Or if you look at it this way, if I have opposite signs, then my rule for opposite signs is to actually subtract their values, their absolute values. So remember, the absolute value of 7 is 7. The absolute value of negative 5 would just be 5. And the same thing in the bottom example there, that the absolute value of negative 7 is still 7. and the absolute value of positive 5 is 5. So in both scenarios here, I'm just taking 7 minus 5 to get 2 because they're opposite signs. That's my rule, is the opposite signs means I subtract their absolute value, and I'm going to keep the sign of the larger value. So out of 7 and 5, 7 is a larger number than 5, so I'm going to keep the sign that 7 has. So in the first example, that's why my answer was positive, because my 7 was positive. And in the second example, my 7 was negative, so my answer was negative. In any case, if I had, and it doesn't matter which order they come in, if I have even a smaller integer in front, so let's say I have, let's say positive 3 plus negative 7. Okay, so in this case, again, because they're opposite signs, my 3 is positive, my 7 is negative, so I have to think of my opposite signs rule. In this case, I'm going to take 7 minus 3, which I know is 4, but in order to determine whether or not it's positive or negative, I have to look at my larger value. 3 and 7. 7 is my larger value, so because it's negative, so is my answer. Another way to think about that, I have $3, but I owe 7, so therefore I still owe another 4, if you're looking at it in terms of that money. Let's see, one more example with this. If, let's say we have negative 6 plus positive, I don't know, 10. In this case, again, I have opposite signs, a negative and a positive, so I'm going to subtract their absolute values. 10 minus 6 also gives me 4. But in this case, because my larger value out of 10 and 6, 10 is bigger than 6, 10 is positive, so my answer is also positive. So I'm finished with just 4. Or another way to think about it, if I owe $6, but I have 10, then I'm going to leave that store with $4 still left in my pocket after I paid for my $6 item. So that's adding integers with opposite signs. Getting into subtraction. Subtraction is a little bit trickier. So in order to remember subtraction, there's one trick that, in my opinion, is kind of the easiest way to remember subtraction. Let me give you a couple scenarios first. Let's say I have negative 4 minus 8. Let's think in terms of our bank accounts here. Again, if we're thinking of it in terms of money, negative 4, if my bank account says negative 4, then that means I owe the bank $4. That's $4 that I owe. A little bit different than what we did before, that we weren't putting it together as a total. Instead, I'm trying to take out $8 more. So thinking that I have this, it's positive, thinking that I have this in my bank account, when I go to withdraw $8 more when my bank account is already in the negatives, I'm going to end up even more so in the negative. So I'm going to end up with negative $12 in this scenario. So you can think about it as money. That might be an easy way to think about it. But what happens is a little bit different of a scenario if I were to give you this instead. If instead of minus 8, instead I have minus negative 8, this is going to be a completely different answer. My answer here is actually going to be, oh, no, not positive, negative 4. It's going to be positive 4. And the reason being is because if we're thinking of this in terms of money, then, again, negatives are things that we owe, but I'm subtracting something that I owe. So I'm taking away a debt. So if I am thinking this in terms of money, then what's happening here is my bank account is negative $4, but my bank is forgiving me of a debt. So something I paid $8 for, my bank is saying, oh, actually, you don't have to pay that. We're going to put it back into your account. So with my bank account being at negative 4, and when they put $8 in, my bank account goes to positive 4. So that's why subtraction can get rather tricky if you're thinking of it in terms of money. So your best bet is going to be to remember the phrase, add the opposite. Add the opposite. Because in subtraction, that's another way that you can solve subtraction problems, and it makes it a whole lot easier because all we have to really do is remember our addition rules. Same sign means that we add them together and keep the sign. Opposite signs means that we subtract their absolute values and keep the sign of the larger value. So if I remember add the opposite, this is very, very similar to like in our division of fractions. Remember in division of fractions, we remembered keep, change, flip. And that's what we did, is we kept the first fraction the same, we changed division into multiplication, and we flipped the second fraction, so we were just back at multiplication. All I had to do was remember my multiplication rules. Very similar here. If I remember to simply just change my subtraction into addition, so I'm going to do that on the first problem we have on the screen here. If I change subtraction into addition, I'm going to keep, what I'm doing is I'm keeping that -4 the same. I'm changing subtraction into addition, and I'm going to make the second integer its opposite. So right now it's +8, so its opposite would be -8. So now we just go back to our addition rules, and what I have here are two integers that are the same sign. They're both negative. So because they're the same, my addition rule says that I'm going to go ahead and add them together and keep that sign, and that's where we get that -12 answer. Whereas in the second problem, I'm going to do this on the second problem on the screen here. If I did the same thing, if I change my subtraction into addition and change the second integer, you're always just changing the second integer into its opposite. The opposite of -8 would be +8. So now, sitting back and looking at this addition problem, I have -4 plus +8. So I have opposite signs. And if you recall from our previous examples, opposite signs, we subtract their absolute value. 8 minus 4 is 4. And I keep the sign of the larger value. So since 8 is bigger than 4, I'm keeping the positive. And that's where that +4 comes from. So as long as you remember the phrase add the opposite, anytime you get to a subtraction problem, all you'll have to end up doing at the end is just remembering to go back to your addition rules. So, in looking at another example, let's say we have, I don't know, let's say +5 minus -2. Doesn't matter, what the signs are right now. It only is going to matter when we change it to add the opposite. So if I add the opposite, I end up changing subtraction into addition, changing -2 into +2. Now I end up with +5 plus +2, giving me +7. Whereas had this problem started off as 5 minus 2, well, obviously we know that that's going to be 3, but we could actually apply the same thing. If I remember plus opposite, then we also know that +5 plus -2 gives me +3 because they're opposite signs. So that's the rule for subtraction, is to simply remember add the opposite. It's the easiest thing to remember on that. And now we get to the multiplication and division of our integers, and that's going to be a whole lot simpler. Our rule for multiplication and division of integers is simple. Way to kind of think about this, and I'll write it down just so you guys can remember. If we ever have the same sign in our two, this is the rule for both multiplication and division. Anytime we have the same sign, our answer is always going to be positive, whereas if our sign is opposite, our answer will always be negative, no matter what. So our number will always be the same, so it's not going to affect the answer itself, so the number. This rule only determines what our sign is going to be. So, for example, 5 times 4. 5 times 4 we know will always be 20. But what we just wrote down there is +5 times +4. And yeah, our answer is +20 because they are the same sign. They're both positive. I'm actually going to get the exact same answer if I take -5 times -4. It's still 20. In fact, it's still +20 because they are both negative signs. So we end up getting +20. The only time you'll end up with a negative answer when you're dealing with integers is if your signs are mismatched. So -5 times 4 is going to end up giving you -20. Or if it was reversed, +5 times -4 would therefore also be -20. So that's the only time. Again, you'll see that the answer is always 20, but because, again, the difference is if they're the same sign or opposite signs. Same sign is positive, opposite sign, always negative. And the same rule goes for division. If we were to look at a couple division problems, if I said, okay, well, 25 divided by 5, we know that that's always going to be 5. Again, but it's positive 25 divided by positive 5. Positive divided by a positive is a positive. If these two were negative, I'd end up getting the exact same answer because they are the same sign. The only difference is if I had negative 25 divided by positive 5, mismatched signs equals a negative answer. But 25 divided by 5 will always be 5. So those are our integer rules. So just remember that kind of, as just a quick refresher with addition and subtraction, with addition, not subtraction too. With addition, remember we had those two rules. Same sign means we go ahead and add them together and keep that sign. Opposite signs, we're actually going to end up subtracting their absolute values, taking the difference of their values and then keeping the sign of the larger value. Whereas in subtraction, remember the phrase add the opposite. As long as you remember add the opposite, you'll be good to go on that. And with multiplication and division, remember same sign equals positive answer, opposite signs equals a negative answer. So those are rules for integers. So that is probably the first thing you guys will see on your all's test for pre-algebra is the multiplication, division, addition, and subtraction of your integers. And then you'll run into, as you keep going through the chapter, we'll run into our exponential notation. Exponential notation is simply this. If I have any number, so the green number I'm writing on the screen here, doesn't matter what that number is, we call that our base. Our base, when we have a number written in the upper right-hand corner, we call that our exponent. So the 3, in this case, the red number, is our exponent. What this means, not to be confused with 4 times 3, what this means when I have a number raised to the power of something, in this case I have 4 raised to the power of 3, what that means is I'm going to take 4 and multiply it the number of times our exponent has there. Our exponent is 3, so I'm going to multiply it 3 times. If we had 4 raised to the power of 4, then that would simply indicate that I want to take 4 and multiply it 4 times in this case. So that's what an exponent indicates. It just tells me how many times we want to multiply our base. So what's going to happen is sometimes you may see that on a test. I'll give you guys this exponential form. This form right here where I have 4 times 4 times 4 times 4, that's what's called the factor form. And factor form you don't necessarily have to write out, but you can if it helps you. But what I'm looking for is the answer. So all you simply have to do is go ahead and multiply that out. 4 times 4 is 16, and 16 times 4 gives me 64. So this is the answer for 4 to the third power. You'll notice at the top of your screen, at the top of page 172, if you're following along in your book, it does give us a few rules. And 4 to the third power is technically one of those rules. Anything raised to the power of 3, that's rule number 3 there. Anything raised to the third power we call cubed. So if you ever hear me say, hey, what is 4 cubed? Then you know I'm referring to 4 to the power of 3. Or if I said, what is 6 cubed? Then I know I'm going to take 6 times 6 times 6 times 6. I'm going to multiply it 3 times. So anything raised to the power of 3 is cubed. Same thing with rule number 2 there. Anything raised to the power of 2 is called squared. So if I ever say, hey, what is 5 squared? You guys would be able to tell me you all know that that means 5 times 5. And so that would be, therefore, 25. Rule number 1 is pretty self-explanatory. Anything raised to the power of 1, such as 7 to the first power, is equal to itself. Which makes sense, because 7 raised to the first power simply just means 7 multiplied 1 time. Whereas rule number 4, that's kind of the only one that's a little odd. Anything raised to the power of 0 is always going to be equal to 1. It doesn't matter what it is. If you just have something raised to the power of 0, the answer to that will always be 1. So if I had 7 to the 0 power, my answer is 1. If I had 18 to the 0 power, the answer would be 1. Doesn't matter. So like I said, that's kind of the only one that you have to kind of remember. But on page 172, it goes through some practice there for you. That practice is great. It helps you to really understand those exponents. But remember, on a test, I'm going to ask you for that exponential form, and I want the standard form or the answer. You'll see on page 172, it gives you factor form first. So you have to tell me what that means in exponential form and so on. I will give you ones like on number 1, where it says 5 raised to the 3rd power. That, again, we know is 5 times 5 times 5. 5 times 5 is 25, and then times 5 would be 125. So, again, factor form would be written this way, 5 times 5 times 5, and then the standard form would be 125. But like I said, you all don't have to necessarily write out that factor form if you don't want to. In ones like number two, they give you the factor form first. Like I said, I won't do that on a test, but it's great for practice. Number 2 gives us 10 times 10 times 10 times 10. Since that is 10 multiplied 4 times, we know that that is then 10 to the power of 4. And if I were to actually multiply out 10 4 times, we would get 10,000. Again, not to be confused with 10 times 4, that would be 400. But 10 to the power of 4 is 10 multiplied 4 times, so that would be 10,000. And that's what exponents are. So like I said, on a test, you guys will see this, and I want this. I want that answer. So I'd familiarize yourselves with what exponents are. The next section, it brings us into what's called square roots. So square root, going back to what we said in those rules for exponents, anything raised to the power of 2 we called squared. Well, if I'm looking for the square root of a number, for instance, number 1 in your all's book says, what is the square root of 16? So we put it in this bracket, and what that means is I'm looking for the square root of this number. In other words, I want to know what number squared will give me that number. And again, thinking about what squared means, squared simply is a number multiplied one time by itself. So for instance, in square root of 16, the square root of 16 is going to be 4, because I know that 4 times 4, or in other words, 4 squared, gives me 16. So that's my answer up here. If I'm looking for the square root of 16, my answer is 4. Whereas there are some other ones that are pretty, we're pretty familiar with, like the square root of 25. I know that 5 multiplied by 5 gives me 25. So therefore, the square root of 25 is 5. Some other ones that are there in your book, if I ask for the square root of 81, I know that 9 times 9 gives me 81, so the square root of 81 is 9. You can really find the square root of anything. If you have the square root function on your calculator, you can find the square root of 386.7293, but I won't do that. You guys are going to see ones like you see there on page 173, where your answer is just like we have on the screen here. The answer is something that you guys will see as a whole number. So don't worry about that. Again, the best way to find that is to think of your times tables. And if it goes beyond something, beyond our times tables, like number 4 is the square root of 225, well, I know my times tables by heart up to 12. So I know that 12 times 12 gives me 144. So I know the square root of 225 then is therefore going to be something larger than 12, but maybe not by much. So I can test in my calculator, if I took 13 times 13, I get 169, or 14 times 14, I get 196. So I'm going to go a little bit higher. If I took 15 times 15, there it is, I get 225. So the square root of 225 is therefore then 15. So it's easy to go ahead and guess and check. All you need to do is multiply numbers by itself then. So that's how we find square roots. The next section in Chapter 7 is looking at the order of operations. Some of you guys may remember the order of operations when we were first taught. We were taught to remember the mnemonic device, please excuse my dear Aunt Sally, in order to help us remember the first letter of each step in the order of operations. Some people may not remember, please excuse my dear Aunt Sally. They may not have been taught that way. Some people were taught, I think, to remember just PEMDAS. However you remember it is up to you. But as long as we follow this exact order here, then we have the order of operations. What that means is we want to follow a particular order. When I have lots of things going on in a problem, if I have some addition, some multiplication, some exponents, lots of different things happen in one problem, there's a particular order that I need to follow in order to solve that problem. And it's actually a 4-step process. I know there are 6 letters on the screen here, but it's actually 4 steps. The first step is that P, which stands for parentheses. So anything that has if I have a problem inside of parentheses, so say if somewhere within that problem I have 5 plus 2. Obviously I know that that's 7, but I'm going to solve that first before anything else that's happening outside of those parentheses. That's the first thing I'm going to look for. So even if I have 5 plus 2 times 7 plus 4 squared minus 6, all this, I need to make sure I follow that first step and solve what's in the parentheses first. Step 2 is to solve for any exponents. Now this includes square roots. If I happen to have something in the problem, if somewhere in my problem, if I had, say, 2 times the square root of 16, then before I, do anything in this problem, I need to find the square root of 16. So that goes right there with our step 2 in our exponents. So 2 times the square root of 16 we know would be the same thing as 2 times 4, so therefore that's 8. But we'll take a look at that one a little bit later, or something similar. So looking at what, the rest of our steps here, if I take the next step, step 3 actually is these two together, M and D. M and D stands for multiplication and division. And when I have multiplication and division, that's the next step. When I've solved all my parentheses, all my exponents, I'm looking for these two next. And it doesn't matter which one. Actually, it does. I'm sorry. Division sometimes can come before multiplication, and that's okay. When I'm down to this step, I'm going to go ahead and read my problem from left to right, and I'm going to solve whichever one of those comes first. So a lot of times people think that because M comes before D in our order of operations, in our mnemonic device for our order of operations, that we have to solve multiplication first. So given an example like this, if I had 8 divided by 4 times 2, a lot of people think I have to take 4 times 2 to get 8, and 8 divided by 8, they think this answer is going to be 1. And that is actually a very incorrect answer. Because now that I'm down to this step, and again, this problem up here has nothing to do with what I'm doing down at the bottom of the screen. Actually, with this problem down here, I'm down to just multiplication and division. I'm actually going to read this from left to right. Take 8 divided by 4 first. 8 divided by 4 we know is 2. So I'm going to take 2 and then multiply that by the second 2. So my answer to this problem should be 4. In fact, if you plug this in, some scientific calculators allow you to plug in problems all in one. So if you have a calculator that allows you to plug in a problem all at one time, and you hit enter or equals, you'll notice that it does give you the answer as 4. So keep that in mind as you get to that next step. The same thing's actually going to apply to the last two. A and S down there at the bottom is step 4. So when you get down to when you're just left with addition and subtraction, you're going to read that from left to right. Doesn't matter if addition comes first or subtraction comes first. That's your next step, is addition and subtraction. So in following the one that's on our screen here and looking at just the, what we've got, 5 plus 2 times 7 plus 4 squared minus 6, we have, we'll just go ahead and do that one. So the order of operations says to go ahead and follow that PEMDAS up at the top of the screen, so which means we're going to go ahead and solve what's in our parentheses first. So 5 plus 2 gives us 7. So my recommendation is this. When you have a large problem where you have to do a lot of different operations, I would write what you're left with at the end of each step, because then it kind of helps you to follow each step along the way, and you make sure that you don't leave anything out. So I've solved what's in my parentheses, so then I go ahead and write out what I'm left with. I have 7, that was what was in the parentheses. Now writing out the rest of the problem, times 7 plus 4 squared minus 6. So then the next step is to calculate any exponents that we have there. We do have a 4 squared, and we know 4 squared is 16. So what I'm left with, and I'm going to run out of room here, so I'm going to, let's see, I have 7 times 7 plus 16 minus 6. So then I'm left with the rest of that. So I get down to the third step, which is any multiplication and division. I do have a 7 times 7 there, so I'll write this in red so we can see that it's separate. 7 times 7 we know is 49, so I'm left with 49 plus 16 minus 6. And now I'm left with just addition and subtraction, so I'm going to read it from left to right. In this case, Addition comes first, so I'm going to go ahead and calculate that addition first. 49 plus 16 is 65, and then 65 minus 6 gives us 59. So my answer here would be 59. And that helps us follow the exact order of operations. That tells us we did get a correct answer on that one. So anytime you have a large problem that has a lot of different steps involved in that large problem, I'm just going to grab one out of your all's book. For instance, let's take number 7. I think number 7 was one that some people had a difficult time with. So let's say we have number 7, 10 minus 6 times 14 divided by 2. So only a few things going on in this problem. I've got some subtraction, some multiplication, some division, but I also have a set of parentheses there. So again, remember we follow the PEMDAS, so first step is parentheses. So again, 14 divided by 2 there is 7. So I'm left with 10 minus 6 times 7. So now I'm just left with subtraction and multiplication. A lot of people think that we have to go ahead and take 10 minus 6 first because it's listed first in the problem. But according to my order of operations, multiplication must come before our subtraction. So I do actually take 6 times 7 first, which I know as 42. So I'm left with 10 minus 42. And this is going to kind of get into our subtraction of integers. Some of you guys may be able to look at this and say, oh, hey, if I have $10 in my bank account, but I take $42 out, that now puts me in negative 32. So that would be our answer here. If you're remembering, add the opposite for your subtraction of integers. If you change this to addition, change positive 42 into negative 42, you still get your answer as negative 32 for our answer there. So that's our order of operations. Just remember, if you want to remember PEMDAS or please excuse my dear Aunt Sally, that's the best way to remember each and every step there. In the rest of chapter 7 is where we actually get into some more of our algebra, meaning that we're going to start using letters. And that's what the fun part of algebra is. We start using these letters in place of things that are considered unknowns, things that I don't know what they are, so we just call them by some letter. We'll see that later on in the chapter when I get into word problems. If I'm trying to find how much money Jill has, I may use J for Jill because it's going to help me find or help me remember who I'm trying to solve for as I go through this word problem. You can use any letter, but any letter that we have in any type of math problem is what's referred to as a variable. So as you start looking at these problems where we are solving for unknowns, we did that in chapter 4. The most common unknown is the letter X. And we saw that so often in chapter 4. Again, it's just the most common one. But again, you can use any letter you choose to as your unknown. So we'll get a lot of exposure to that too. Anytime you have a number that's right next to a variable, so say if I put a 5 right here in front of this X, anytime you have a number right in front of it, that number is referred to as the coefficient. What's happening with that number right next to the variable, again, the variable is something that I don't know. I don't know what this X stands for. Later I may figure that out and I may be able to solve this problem. But with the letter right next to the number, that simply means to multiply those two. If I wrote 5 plus X, obviously I know that I'm going to take 5 and add it to X. 5 minus X would be written this way, and 5 divided by X would be written this way. But anytime I want to multiply, this is an easier way to do that if you just write them right next to each other. Again, X is the most commonly used variable, so a lot of times we don't want to say 5 times X, because then if you see that here, we have 5xx, and that looks pretty confusing. So in pre-algebra, we decided, or whoever invented this a long time ago, decided that it was easier to just put them right next to each other and say that means to multiply. So remember that as you go through these problems. Anytime you see a coefficient right next to the variable, that means to multiply those two. So there's a couple things you guys can do with these variables. If you flip over to page 176, what you can do is you can take certain word phrases and turn them into algebraic expressions. These algebraic expressions allow us to kind of see step by step as to what we're looking at. For instance, let me show you what I mean. Number 1, we have some number p decreased by 4.5. Earlier on in the chapter, we were looking at certain words that indicated whether or not we're dealing with positive or negative. We can use similar word phrases to help us see whether or not we're dealing with addition or subtraction or multiplication or division. So number one, some number p, that's our unknown. So we just write the letter p, that's our variable. And when we decrease something, we are subtracting. So we are decreasing by 4.5. So this algebraic expression would be p minus 4.5. There's a couple things, like I said, we're going to be able to do with these algebraic expressions later on in the chapter. Later on, I may say, hey, if I know what p is, if I said p is equal to 10, then therefore I would be able to plug that in and solve for this problem. Easy. I may also, later on in the chapter, I may say, hey, I know more than that. I may say some number p decreased by 4.5 is equal to 8. If that's the case, then later I should be able to figure out, if I know that p minus 4.5 is equal to 8, then from there I should be able to figure out what that p is. So we'll get to that later on in the chapter, but for right now we're just writing expressions. We're just simply stopping at this point and taking these word phrases and turning it into these expressions. So going through a couple other examples. Number 3, the sum of two numbers a and b. Sum is to add those together. So that would simply be written as a plus b. If I get into number 5 says the sum of two numbers a and b. So exactly what we have on the screen there, just that a plus b. But it says, pay close attention to this on number 5. It not only says the sum of two numbers a and b, but it says the sum of two numbers a and b then divided by 6. So the tricky part about that is if I wrote a plus b divided by 6, then I run into a slight issue. Because yes, this is the sum of two numbers a and b divided by 6 in our eyes. But if I were to plug this into a calculator, remember, some of our calculators are programmed to understand the order of operations. So what would happen is our calculator would actually do this first, because we know that division always comes before addition. So what has to happen if I write it this way? I have to do this. These parentheses tell me exactly what that word phrase is telling me. It wants me to find the sum of a plus b first, then divide it by 6. Another way that you could write this expression is a plus b over 6, which indicates the same thing. But when it's written on top of the 6 like that, I have to find the sum of a plus b first before I can even divide it by 6. So either one is correct in writing this algebraic expression here. Number 7, the quotient of some number r and 3. The quotient means division. So if I'm trying to find the quotient of two numbers, this one said r and 3, I'm dividing. So it'd be r divided by 3, or r over 3 would indicate the exact same thing. So that's what we're doing. Those are algebraic expressions. We're going to focus more on those a little bit later as we get into then equations. I had also mentioned with these expressions, I may be able to later, if I could tell you what those unknowns were equal to, I could figure out the rest of the problem. I could solve the problem. I used the example earlier. If I said, hey, p minus 4.5, that was our very first expression that we wrote. But if I came in and said, hey, I know that p is equal to, I think I said 10, then if that's the case, I should be able to plug that value in right here and solve the rest of this problem, because that algebraic expression then says 10 minus 4.5, which is 5.5. So I can solve it. And that's what's happening on page 177, that I'm able to take these algebraic expressions and substitute. This is called substitution. I can substitute these values in if I know what they're equal to. So looking at page 177, practice 16, numbers 1 through 5 there, you'll notice that they use the variables a, b, and c. In those expressions, all those expressions we have listed there, it says in the directions to use 5 for the letter A, 4 for the letter B, and 1 for the letter C. So anywhere we see these letters, I'm going to substitute those values in. So looking, for instance, at number 1. Number 1 says 4a squared. Now, anytime we have a variable, anytime we have an exponent on a variable, it is attached to that variable. So whatever a is, we are going to square it. We would only take, well, I'll have to give you an example a little bit later. That 2, that exponent, is only attached to the a. It's not attached to the 4 in any way, shape, or form, unless we saw something like this. If we had this in parentheses where it said to take 4 times a first and then square it, that's what we would do. But because that squared, or that 2, is right next to the a, then we are going to square whatever a is, which we know is 5. So what this problem says, again, remember when a coefficient is written right next to a variable, it means to take that coefficient and multiply by that variable. But again, we know that that variable is 5. So what this problem actually says is 4 times a squared, or in other words, 4 times, and I'm just going to write a little dot to indicate that that means times, 5 squared. There's a lot of different ways you can substitute values in. Some people choose to use parentheses to show, hey, there's that number. Instead of just plugging it in as 4 times 5 squared, sometimes that makes it look like 45 squared, so I choose to not use that. But either one of these is totally fine, so you can see it a little bit better and show that this means 4 times 5 squared. If you even wrote 4 times 5 squared, that's totally fine. However you substitute it in is totally up to you, as long as you know that it's not 45 squared. But we do need to follow our order of operations to solve the rest of this problem. And when we do that, 4 times 5 squared, what we need to do is think, okay, parentheses. Now, when I say parentheses, if you're substituting your values in this way, that's not an operation inside of parentheses, so there's nothing to solve inside of that. That just simply says 4 times what's in those parentheses, so we're not solving anything within there. The next step is actually exponents, so I'm going to take that 5 and go ahead and square it, and we know 5 times 5 is 25, so what I actually have here is 4 times 25, and 4 times 25 is 100. So that's all we're doing, is just substituting those values in. It's the same way we use a formula, that all I need to do is plug those values into that particular formula. So same thing with number 2. Number 2 says 5a squared b, which is the same thing as 5 times a squared times b. And again, all we're doing is plugging those values in. It says a is equal to 5 and b is equal to 4. So we plug those right in. So this actually says 5 times 5 squared times 4. So I'll plug those in accordingly. 5 times 5, I'm just plugging them in, squared, times 4. So you can see what's written in blue. I've just plugged in substituted in our variables. So following the order of operations, our exponents come first. So 5 squared is 25, so I'm left with 5 times 25 times 4. It's all multiplication. If I were to multiply those 3 numbers straight out, I get 500. So that's our substitution. That's one thing you can do with those variables. If you figure out what those variables stand for, you just plug them right in. So later on, what we're going to look at, so on page 178 and getting over on to page 179, we can do the same thing. What I can do is take, instead of just using random word phrases that say some number p minus 4.5, I can take actual situations like on page 179 and take those and put them into algebraic expressions as well. So given an example on page 179, it says, Robert had 2 fewer cavities than I had. It doesn't say anywhere on that word phrase how many cavities I had. So therefore, I'm the unknown. I can either be written as X, or I may write E for Ellie as the unknown, or C for cavities. Again, it does not matter what letter you choose to use as your unknown, as long as you use some type of variable. So let's say I wrote C for cavity. That was the last one I wrote, so I'll just use C for cavity. That's how many cavities I had. So in writing a word phrase for Robert, that's what I'm looking at here, it says Robert had 2 fewer than I had. So if C stands for the cavities that I had, he had C minus 2 because he had 2 fewer than what I had. So that's our word phrase, or that's our algebraic expression for number 1 is C minus 2. Same thing with number 2. It says I doubled my income after I finished the certificate program. When you double something, you multiply it by 2. So I'm going to take whatever my income is, so that's my unknown, my income, I'll use I for income, and I'm going to multiply it by 2. The most common way to write this, again, is what we looked at earlier, is the coefficient written right next to the variable. So 2i would be good here, but I'll take anything if you're given these word phrases, as long as you somehow show me that it's I multiplied by 2 or 2 multiplied by I. So that's how we take these situations and turn them into algebraic expressions. So with solving equations, I had mentioned this earlier too, that with these expressions, what I can also do if I said, oh hey, we have some number p decreased by 4.5, but I know that whatever p minus 4.5 is equal to 8. Well, then therefore, with that being said, I can then figure out what p is equal to based on that. So here's how we do this. Anytime you're solving for an equation, what you want to do is you want to be able, let me try to erase this here. Oh, it's not working. What I want is to think of everything according to this equal sign. Okay, so over here where the P is, I'll call that the left side, and over here where my 8 is, I'll call that the right side. Over on the left side of the equal sign, I want this problem to say simply just P is equal to something. That's how we solve for it. I'm trying to figure out what P is. But right now, as you can see up at the top there, it says P minus 4.5 is equal to something. So what I need to do is I need to get rid of that 4.5. And in order to get rid of something when you're trying to solve for a variable, you have to do the opposite of what's being done. And what I mean by the opposite of addition is subtraction, and vice versa. The opposite of multiplication is division, and vice versa. So in this case, because 4.5 is being subtracted, what I'm going to do is I'm going to add it, and what that will do is it will cancel those 4.5s out. If I'm taking, a number that's being subtracted and I choose to add it, it cancels out that number. But you have to remember what this equal sign means up here. This equal sign means that the left side is equal to the right side. So if I do anything to that left side, like I just did, I'm going to have to keep it equal. So therefore, I'm going to have to add 4.5 to the right side as well. So yes, over on that left side, it did leave me with P by itself because I didn't do anything to that P. So there it is down at the bottom, just P hanging out. But over there on the right side, I have 8 plus 4.5, which we know is 12.5. So this tells me that P is equal to 4.5. So when I'm solving for any variable, that's all we have to think of is just do the opposite of what's being done. So given another example, let's say we have, and I'll just use x because it's a common variable. Let's say we have x plus 5 is equal to, and I'll think of an easy one, x plus 5 is equal to 15. Well, we know that 10 plus 5 is equal to 15. But how do we figure out that that's 10? Well, over on the left side of that equal sign, I need to get rid of that 5 because I want it to say, again, I want it to say x is equal to something. In this case, like I said, we know it's going to be 10. But right now it says x plus 5 is equal to something. So I have to get rid of that plus 5. So I do the opposite. Because it's, 5 is being added, I go ahead and subtract it. And I must do the same thing over on the other side of the equal sign. Over on the left side over there, my 5s have canceled out. But over on the right, I have 15 minus 5, which we know is 10. And don't forget, you can always, if you're ever unsure, you can always, this tells me that x is equal to 10, so if I plug that into my original problem, if I said 10 plus 5, would that give me 15? Absolutely. So then therefore we were correct in solving this problem. Looking at another one, if something is being multiplied, so say if I have 5x is equal to 10, and this tells me that 5 times something is equal to 10. Well, again, that's one you can easily do in your head. I know that that's going to be 2, because I know that 5 times 2 is what gives me 10. But in solving this, and the way that we know how to solve this, I have to do the opposite of what's being done. So because x is being multiplied by 5, I must divide by 5 in order to get rid of it. That's how we cancel it out. Leaves me with x over there on the left. But I have to keep it equal, so I have to do it to both sides. And over on the right side, I have 10 divided by 5, which we know gives me 2. And the opposite goes for if something is being divided. So if I have, let's say, x divided by 4 is equal to 10, then, again, I know that that's going to be 40. But in order to figure that out, what I have to do is, because x is being divided by 4, in order to get rid of the 4, I must multiply by that 4, and I must do it to both sides. So over there, the 4's cancel out, leave me with x. And over on the other side, I have 10 times 4, which gives me 40. And that's how we solve for any unknown, if I'm trying to figure out what the unknown is according to an equal sign. Now, keep in mind too, this isn't listed in your book, but you may come across this in the next section. If you ever happen to see 2 things being done to an x, or being done to a variable, I shouldn't say x, but any variable. For instance, if I have 2x plus, let's say, plus 5 is equal to 10, then again, here's my equal sign. Over on the left side of the equal sign, I have 2 things on my variable. So what I must do is, in order to get rid of that, what you need to do is get rid of whatever's being added or subtracted first. We're kind of thinking in opposite of those order of operations. So I'm actually going to the addition and subtraction first in this case whenever I'm getting rid of numbers. And I am getting rid of that 5 first. So again, I'm still going to do the opposite. I'm going to subtract 5, and I'm going to subtract 5 on both sides, just like we've done before. What it does over on the left side, it cancels out my 5s, and it does leave me with that 2x. I still haven't done anything to the 2. But over on the right side, it leaves me with 10 minus 5 is equal to 5. So then now what I must do is I just end up with a 2-step problem. My second step is to get rid of that 2. And we know that, when 2 is being multiplied, in order to get rid of it, I must divide by 2. And I must do it to both sides. Over on the left side here, it cancels out my 2's, and it does leave me with x finally. And over here on the other side, 5 divided by 2 gives me 2.5. So remember that. Always get rid of whatever's being added or subtracted first if 2 things are being done to x. So given another example, if I said, okay, well, we have x divided by 3 minus 6 is equal to, I don't know, let's say 20. So again, get rid of whatever's being added or subtracted first. So what I'm going to do is I'm going to choose to add 6 to both sides. What that does is it leaves me with x divided by 3, because I haven't done anything to that x over 3 yet. And over on the other side, it leaves me with 20 plus 6, which I know is 26. And then now I just need to get rid of that 3. Because 3 is being divided, then what I must do is multiply it, and I multiply it on both sides. So 3's cancel out over here, leaving me with x. But I also multiply by 3 over here on the right side, and 26 times 3 is 78. So my answer is 78. Here is a prime example of where it's really going to be important to go and double check your answer. By plugging your answer into the original problem, if x is equal to 78, then that means I can take 78 divided by 3, which is 26. 26 minus 6, does that give me that original answer? Absolutely. We know 26 minus 6 is 20. So that means we did this problem correctly. So just remember that in solving for x, we always want to do the opposite of what's being done. If 2 things are being done to that same side of the equal sign that our x is on, in order to get x by itself, we have to get rid of whatever's being added or subtracted first, if you ever run across anything like that. And the last part of your all's chapter is to kind of take everything that we've done in this chapter and put it all together. In this case, we have word problems instead of word phrases, so we're doing the exact same thing, except the difference is instead of just phrases They are actual word problems, and we're going to turn them into equations instead of algebraic expressions. So we will have that it's equal to something instead of just p minus 4.5. We'll have p minus 4.5 is equal to something. So for instance, if you take a problem like number 2 on page 181, number 2 says, if a patient's pulse decreases by 8 beats, it will be 78 beats a minute. How many beats a minute is the pulse before the decrease? The easiest way to take these and turn them into equations is, remember the question being asked. What that's doing is it is always asking us for the variable. So the question itself simply just says, how many beats a minute is the pulse before the decrease? So I'm going to go ahead and use P for pulse. And this tells me I'm looking for, this stands for, sorry, I didn't mean to write that. Well, I can't write today. This tells me that this P stands for the pulse before the decrease. Pulse before the decrease. So that means everything else I do to this P, I have to go according to whatever that is before the decrease. So reading the rest of this part, the first part of that problem, it says, if a patient's pulse decreases by 8. So again, that's what I'm going to do is I'm going to take that P and decrease it by 8. And how we decrease anything by 8 is I subtract 8. And then here's where the equal sign comes in. It says if we decrease it by 8, it will be, so there's that equal sign, 78 beats a minute. So there's my word problem that I've taken and turned into an equation. So a patient's pulse decreasing by 8 beats a minute will be 78. So in other words, P minus 8 is equal to 78. So what it wants us to do then is derive a solution from that. And we know how to do just that because P is, we're subtracting from P. We're subtracting 8 from P. So therefore I'm going to add 8 to both sides. And that leaves me with P on one side and 86 on the other. So therefore the pulse before the decrease is 86 beats a minute. Doing another problem. Let's take a look at, see, number 5. Number 5 says, Den has 7 more patients to care for than 1. If Den has 18 patients to care for, how many does 1 have? So in reading that question, because it is asking me for 1, I use J for 1 because that's my way of reminding myself you're solving for 1 here. So not Den. So not to get the two names confused, this helps me to see that. So if a patient's pulse decreases, I'm going back to read the whole problem again, I'm sorry. Den has 7 more patients to care for than 1. So whatever 1 has, that's my unknown there, but Den has 7 more than that. So in other words, he has 1 plus 7. So he has 7 more to care for than 1, and he has 18 patients. So there's our equal sign coming in again. He has 1 plus 7, and that equals his total amount of patients at 18. So in order to figure out how much 1 has, I'm going to have to do what we've done before. I'm going to have to do the opposite of what's being done. So I subtract 7 from both sides. Cancels my 7s out over on the left side, leaving me with J. Over on the right side, I have 18 minus 7, which is 11. So therefore, 1 has 11 patients. So I hope that helps. I know that's just a couple of them, but that's kind of a quick summary, or hopefully it was a pretty good summary of the entire chapter. You guys know, as always, please feel free to call me anytime you need me or email me if you guys have any questions on anything. Thank you.